Greetings, in this one let's talk about complement graphs. They're also called inverse graphs, but it doesn't really matter. Complement is more used as a terminology in this case. So let's say this is our example here. I'll call it graph G. It has two vertices, one to connected, the free one is disconnected from them, but all these three vertices make up this graph G. And if I want to have a complement of this graph, that's what we're talking about, I can denote it G bar, or let's say I call it H in this case, and the complement will basically be defined as follows always. When there are edges in the official graph, just take the same vertices. So I'll actually draw the vertices first. Take the same vertices, so 1, 2, 3, even the names and the same positions, I put them so it's very clear that we keep the vertices the same number, and I'll even draw it in the same spatial way. Take the same vertices from the original graph, and to create a complement graph, remove any edges that there were, and only put there those edges that were missing. So any possible edges. Now imagine a complete graph. Imagine a complete graph where any two distinct nodes were adjacent, meaning there's an edge connecting them, and basically draw that, but then remove any of those edges that were in the original graph. So that means that basically I will leave out this edge in this case, and all the other possible edges between the nodes we have here, I will put there. So 1, 2, that edge is not there, but 1, 3 and 2, 3 will be there. So that's that. So this is a graph complement. Just that edge that was not in the original graph, add it there, and that edge that was in the original graph, remove it, compared to the original one. Now a definition, let's say complement of graph G is graph H, and basically the vertices set of G will equal the vertices set of H. But one thing to keep in mind, for any UV belonging to the vertex set of H, so any two nodes, any two vertices of the H, UV, so that H made up edge between these two vertices, denoted UV, will belong to the edge set of H, if and only if it doesn't belong to the edge set of G. So basically what it sums up here is, we have the same vertex set, the same vertices, you see 1, 2, 3, 1, 2, 3, but what's changed is whenever, if and only if, so exactly when there is an edge in H, it must not be in G, which is also the truth. And also, you see, G is a complement of H. That's why it works, right? Both ways. So this is if and only if, both sides implication. It can go both ways, from G to H, from H to G, that idea. You see, complement of this one is this. You remove these two edges and add the only missing one, the 1, 2. Or when you're going from G to H, you remove this one and add the other two. So that's that point. And one more interesting thing, now this is an example, we can draw many more examples with, for example, bigger graphs. But one more thing I want to note here is an interesting fact, and that is as follows. We'll divide the board to have some space, but it doesn't really require that much. Let's take just another example for this. So let's say we have another disconnected graph. Actually, we could have used that one. So I'll actually use that one. Let's say we have this three vertex graph, and we had these two connected. They were called 1, 2, 3. And there is a rule, and that says if the original graph, so let's say this is again G, is if G is disconnected, then H, which is the inverse or a complement graph. By the way, it's also denoted complement graph is denoted in general as the original graph's name with a bar, for example. But I call it H here, right? So H was the G bar. So I can say that this is our use notation here, and we are really talking just about the H like we used before. So the complement H is this disconnected H, then the complement H is connected. Connected. Well, we already had the complement, right? We had the complement, and the complement was namely this. So yes, that's true. This one is connected here. So this one is connected, and this one wasn't connected. We had this and this, these two disjoint parts. But here we have one graph where we can have a walk from any vertex to any other vertex.